A lesson on precision and accuracy, and a lot of people think that they are the same, but they are not. Let's first look at our unit organizer and see where we've been. Remember that we started off learning where the metric system came from, where the English system came from, how to convert between the different units, and now we're going to look at how accurate and precise measurements are. So we're learning all the different components of what a measurement is all about. Today's goal is to understand the difference between a data set's precision and accuracy. The big idea is that researchers need to understand how good their measurements are. They do this with understanding the precision and accuracy of measures. And a lot of times there's going to be arguments between scientists as to how accurate and precise those data sets are. But right now, on your own, read the article on precision and accuracy in your packet and go ahead and summarize the article in 2 or 3 sentences. So please pause the video at this time if you have not yet done that. Here's how I would summarize the article. Precision can be defined in one of 2 different ways. The first way is how many decimal places are in a single number, or how close the numbers of a set are to each other. In other words, the second definition is how big is the range of data. Now please remember, with these 2 definitions, the first definition refers to one single data point. The other definition refers to an entire set of many data points. Also, there is nowhere in these definitions anything about how close the answer is to the correct answer. It is only in relation to the other data points. Accuracy is how close a number is to the correct answer. But notice here that in accuracy, they don't say anything about how many decimal points your answer has or what the range of data is. So accuracy and precision are different things. Accuracy is often judged by how close the average or the mean of data comes to the truth. Remember that mean is just a fancy word for average. Accuracy is found by this equation. The percent error is difference over the correct value times 100. Now the difference on the top, that is the difference between your data point and the correct answer. So let's have an example here. A team of students measure the period of a pendulum to be 1.3 seconds. The equation says that the period should be 1.5 seconds. What is the percent error in the student's timing? So we use our equation again, difference over correct times 100. The difference is 1.5 minus 3. This is what the equation said it should be measured at, and the 1.3 is what the students actually did measure, and down at the bottom is the correct value from the equation work. So we get 13.3%. An instructor says that an A+ lab has less than 4% error. If the result of the lab should be 15.24 meters, what are the highest and lowest results that will receive an A+? To do this, we start off with the idea that we're aiming at 15.24, and we can be either 4% too high for some upper value, or 4% too low to get a lower value, but the A+ is somewhere within this range. What we need to figure out is how many meters is 4%, and then we'll add that to get the upper value, and we will subtract off that number of meters to get the lower value for an A+ grade. So the difference here is what we're looking for. We know that the percent error is going to be 4%. We know the correct value is 15.24. So we're looking for the difference. And we find out that that's 0.6096. We're going to round that to 3 digits, 0.610. So to have the value that would be just a little bit too high for an A+, I add the 0.61 to our correct value. And so 15.85, that's the highest that you can get on your measurement and still get an A+ grade. And now we're going to subtract that in order to get the lowest value for the A+ grade. So we take our correct value minus the 4%, and we get 14.63. Okay, now we're going to look at how precise can you measure something and still be a legitimate scientist. The ruler below is marked in millimeters. How would you read it to the greatest precision? Now, when I say that something is marked in millimeters, that means that each tiny little mark is a millimeter. So this would be 5 millimeters right here, and this would be 10 millimeters, and 10 millimeters is the same as a centimeter. So I can label the centimeters like that if we wanted to. So now, how would I read the tip of this lightning bolt? Well, it's more than 2, and it's more than 2.8. It's a little bit more. So what I do is I estimate how many tenths of a degree across there is. So I'm going to say that it's a little bit less than halfway. So it's less than 2.85. I'm going to guess it's going to be 2.83. Now somebody else might say it's 2.84 or 2.82, and that's all fine. We can have disagreements about exactly what our estimate is. But I would not want to say that it's 8.23157. That's claiming better eyesight than any human really does have. We can estimate to the nearest tenth between increments. So one more decimal point in this case. The ruler below is marked in centimeters. How would you read it to the greatest precision? Okay, so in this case, it's marked in centimeters, so the tiny marks here are each individual centimeter. So if I put numbers on this, I'd have it like I have shown here, 5, 10, 15, 20 for the big marks, 1, 2, 3, 4 for the tiny marks. So this rod, it is more than 20, it's more than 24, but it's less than 25. So it's 24 point something. And putting in that red line, I can see that it's more than halfway. I'm going to say it's 24.6. Again, somebody might say 24.7. Somebody might say it's exactly 24.5. I'm not going to dicker about little tiny things like that. It's an estimate. Each person will be a little bit different. I would say that 24.8 would be a bad estimate. 24.1 or 0.2 would be bad. This thermometer is marked in degrees. How would you read it to the greatest precision? Okay, so the mercury is right down here, somewhere along in there. It's between the -2 and the -3. But remember, we're on the negative side of things here on this scale, and so it is more negative than just simply -2. It's going to be -2 point something. Some people get mixed up and they say it's going to be -3 point something, but that's the wrong side of the scale. So it is pretty close to -3. I'm going to say -2.8. Again, you can have your own version of that, but don't say it's -2.85 or -2.89. It's only one decimal point that you can estimate between -2 and -3. For those of you who are in regular physics, your lesson is now done. You may turn off the video and go on to your homework or other stuff. Honors folks, you are going to go on to these more complicated problems. This beaker is marked in increments of 50 milliliters. Each mark here is 50 milliliters. How would you read it correctly? This is a little bit more complicated. We can't just add one more decimal point to our answers. We have to do a little bit of calculations. The first step is to estimate the tenths above this increment that's closest to the surface level. So I'm going to guess that this water level is about 2/10 of the way from the lower increment to the one that's above. The second step, calculate the number of milliliters then above the mark. If this is 2/10 of the way above the mark, how many milliliters is it above the mark? So I multiply 2/10 times the 50 milliliters that each mark represents, and so I'm going to estimate that there are 10 milliliters above this mark here. Then the third step is to add that 10 milliliters to the increment below it. So it's going to be 10 plus 150. We're going to say it's 160 milliliters in that beaker. Okay, protractors. They are often marked in increments of 2 degrees. How would we read this one accurately? I should say precisely. First step, estimate the tenths above the lower increment, and I'm going to estimate that it's 6/10 of the way between the 34 mark and the 36 mark. 6/10 of the way across. So how many degrees above the 34 is that? Well, I multiply 6/10 times the 2 degrees for each mark, and so I get 1.2 degrees above the 34 degree mark. So the final answer then is we add the 34 plus 1.2, and we get 35.2 degrees. That is the end of this lesson.